Hi, I'm Kian. In this video, I'm going to show you how to find the basis of the kernel and the image of a matrix. So this is the first few videos of the linear algebra playlist, and we want to focus on linear transformations, kernels, and the image. Just a brief description: the kernel of a matrix is basically the domain of kind of the subspace of the matrix, and image is basically the codomain of the subspace. And the basis basically is a subspace, is a set of basically vectors that spans, in this case, the kernel and the image. And a unique fact about the basis is that all of the vectors that are in the basis are something called linearly independent. And that means that basically we cannot write them, those vectors, in terms of each other, in terms of basically constants that are not zero. If two or three vectors are linearly independent, then, for example, we can't write them in terms of linear equations linearly to describe each other. So that's the neat fact about the basis, is that all the vectors in a basis are linearly independent from each other. So let's go through the process. So how do we find the kernel of A? So by definition, to find the kernel of A given a matrix A, we have to first solve the basically homogeneous equation A times vector x equal to the zero matrix, or zero vector in this case. And here we have a 3x4 matrix, and since this matrix is not invertible, we have to go through the RREF process, or the row reduced echelon form. Now, I'm not going to go through all the process. Now I'm going to cut short and tell you what the answer will be, but I'm going to make a separate video, which I will go through sample examples of how to go through the whole process of basically writing the matrix in the row reduced echelon form, which is really important in linear algebra. But if we basically do all the calculations and go through the RREF process, what we get as the matrix A is basically, after doing the RREF process, is the matrix 1, 0, 0 as the first column, 3, 0, 0, 0, 1, 0, -1, 4, 0, and 0, 0, 0 at the end, because we're basically setting it equal to the zero vector. Now, what does this mean? So basically, this is a linear equation. This is a system of linear equation that has been written in the matrix form. We've done the RREF and we found this. Now, what I'd like to do is basically write out what we have now. So after doing the row reduced echelon form, what we have for the first row is that, so each row basically is an equation. So the first row is basically the fact that x1, so I'm going to say basically there are 4 variables in this case. So we start with 4 variables, 3 equations. So after doing the RREF, we get that x1 plus 3x2, because these are all the coefficients. We have no x3 because it's 0, and then minus x4 is equal to 0. And we have a second equation, the second row, that is x3 plus 4x4 is equal to 0. Now the fourth equation is just all zeros, so it's easier for us because we only have 2 equations. Now, what do we do? So now we have to basically solve this in terms of parameters. Since there are infinitely many solutions to this set of equations, we can parameterize it. So how do we do it? So basically, I'm going to change colors. So we can, for example, let x2 to be t. And I'm going to let x4 to be s. Now, by definition, if we solve for it, x1 would be s minus 3t, and x3 would be minus 4s. Now, how can we better write this equation? So if you want to write it in the kind of a vector form, we can write that the vector x, or I'll write it here, can be written as basically written as I'm going to factor out a t, so we have t times the column vector. So in x1 we have 5 minus I'm sorry, not 5, s minus 3t. So the coefficient of t basically is negative 3. For x2 the coefficient of t is 1. For x3 there's no t because it's all negative 4s, so 0. And for x4 there's s, so also 0. So that's the first vector. And then we add it to s, so we factor out the s, and then multiply it by, so x1 there's 1s because there's s minus 3t. For 2 there's no because it's t. For 3 is negative 4, and for x4 is 1. So now we can see that the basis, or the kernel that we want to basically write as a basis, is a span of 2 column vectors, and these are the 2 column vectors. So if we've solved the homogeneous equation, we've got these 2 column vectors, so our job is really easy. For writing the basis, let's say B, which is the basis of a kernel, this would be just the span of these 2 vectors. So negative 3, 1, 0, 0, and 1, 0, negative 4, 1. So that's all what you have to do. And in fact, if you want to go a step further, and for example, a question on the exam asks us how do we find, for example, the nullity of matrix. So what the nullity is basically the dimension of the kernel. So you found a kernel, we've written as a basis of 2 column vectors. The nullity is by definition the dimension, which means how many vectors are in our basis for the kernel. And in this case, there are 2 vectors, so the nullity of A is equal to 2. So that's how we find the basis for kernel and the nullity. Now let's go towards the basis for image. Now how do we do that? Now it's very similar. It's actually no more extra process needed because again, we have to also go through solving this homogeneous equation and going through the row reduced echelon form. But for the image, it's a span of basically the column vectors, and basically it's a codomain. So initially, we start with this matrix A. So our initial image, or image of A, is the span of all these 4 vectors. The vector column vector 1, which is 1, 2, 1, column vector 2, column vector 3, and column vector 4. However, since we want to write the basis, we have to make sure that all of those 4 vectors or column vectors are linearly independent. And so when we go through the RREF, the only vectors that we want to keep as our basis of the image are those with the leading 1. That's because those are the ones that are linearly independent. And if we go through the process that we went through to find the kernel, we can see that there are definitely linearly dependent vectors, which means that we can basically omit certain vectors and we don't really need them to write the basis for the image. For example, here we see that after doing the RREF, the only 2 columns that have a leading 1 are the column 1, which is 1, 0, 0, and column 2, which is 0, 1, 0. And in fact, we only really need the column on column 3, I'm sorry. And in fact, we only really need column 1 and column 3 to solve the rest, because if you have column 1 and column 3, for example, we can solve for column 4 and we can solve for column 2. So we don't really need them, the column 4 and column 2. So in this case, the basis of the image, again, it's a good thing to remember, is that after we do the RREF, is the columns that have a leading 1. In this case, this is this column and this column. But we don't write it as 1, 0, 0, 0, 1, 0. We go back to the original matrix. So in this case, the basis for image, I'm going to write it B sub 2, let's say, this is 1, is a span of these columns. It would be column 1, because we said it's after doing the REF, it has a leading 1, so it would be 1, 2, 1, this column vector, and the column vector 3, because also it has a leading 1 after doing the REF. The other 2, column vector 2 and 4, are linearly dependent, so we basically omit them in the written basis for the image. And we have 0, -1, and 1. And it is similar to finding the basis for a kernel. If they ask us what is the rank, again, these are good terms to know. The rank of this matrix A is basically the dimension of the image of A, which means how many vectors are in the span of the basis for the image, and in this case, it's also 2. And in fact, another good thing to remember is a theorem called the rank nullity theorem, in which it states that the rank of a matrix plus the nullity of the matrix, or if you want to write it another way, we can write as the dimension of the image plus the dimension of the kernel is always equal to the dimension of the domain, which is basically the rows, which is basically the columns of the matrix. So the original matrix is a 3x4 matrix, so it's an m by n matrix. So the dimension of the domain is the n, which is 4. And in fact, if we add the nullity to the dimension of the image,